All right, so now we're getting into the part of the year where your life gets a lot easier. No more doing instantaneous rate of change with that limit process. Now we're going to be able to find the slope of the tangent line, the instantaneous rate of change, aka the derivative. Now we're going to be able to find it really quickly. Let's learn some derivative rules, right? This packet is going to teach us all the derivative rules. We're going to start off with the power rule. Then we got some other rules, constant multiple rule, and we got the sum and the difference rules. Well, basically all the easy rules at first, and then we'll deal with the multiplication and the division and the composition a little bit later. Let's do the power rule first, right? So here you can see at the top right, up in this area, I've got some examples already written down for you. I have, hey, if your original function is x to the fourth, the derivative would be 4x cubed. If your original function was x to the 11th, then the derivative would be 11x to the 10. Or if your original function was x to the 90, then your derivative would be 90x to the 89, right? Hopefully you can see the pattern, but generally what happens when you're taking derivative is this exponent is going to multiply down to the front. It's going to become the coefficient, and then that exponent is going to decrease by 1. That's it, right? Taking a derivative seems like it should be harder. It's not. It's that easy. The exponent multiplies to the front and then decreases by 1. 2 steps, really easy. Let's write the rule. In general, if you have any power term, so x to any power, that exponent is going to multiply it to the front, and then it's going to decrease by 1. So your derivative would be n times x to the n minus 1 power, right? The exponent multiplies to the front, decreases by 1. Let's practice. Here we go. X cubed. That 3 multiplies to the front and then decreases by 1. Very lovely. Next one, you have a square root of x. You probably want to rewrite that as x to the 1/2 power. That's a power term, right? Fraction exponents are still exponents. So that 1/2 is going to multiply it to the front. And now be careful, subtracting 1 should not ever be hard in any context, but subtracting 1 is going to cost you some points in calculus, right? 1/2 minus 1 would be negative 1/2. Be careful when you subtract 1. If you wanted to, you could rewrite this as 1 over 2 x to the 1/2, right? That negative exponent means it's going to go to the bottom. And you could also rewrite this as 1 over 2 roots of x. That's a derivative that comes up so quickly. If you can just memorize, hey, if your original function is a square root, the derivative is 1 over 2 square roots. That'll just save you some time later on. It is just the power rule, so if you have to keep reproving it, that's fine. It doesn't take too long. But if you can just memorize it, it's in your best interest. Another one that's really common, I'm going to deviate. I'm going to go wildly off script here. Another one that's really common is the reciprocal function. If you have 1 over x, which you could rewrite as x to the negative first power, then your derivative, that negative 1 would multiply to the front, and then negative 1 minus 1, so that new exponent would be negative 2. So here's another one that's pretty common. If your original is the square root, then your derivative is 1 over 2 square roots. And then if your original is the reciprocal 1 over x, then your derivative would be negative 1 over x squared. Again, those are just 2 power rule derivatives that come up so frequently, you may just want to memorize them. Anyways, a little bit extra. Here we go. Next one. T on the bottom to the 4th power. Let's rewrite it. So it'd be t to the negative 4th power. Got to rewrite it as a power term before you can use the power rule. That negative 4 is going to multiply to the front. And be careful, this new exponent is not negative 3. Right? Be careful when you subtract 1. Negative 4 minus 1 is negative 5. And if you wanted to, you could rewrite that as negative 4 over t to the 5th. Sure, I'm going to box the answers. Why not? Now the next one, you're like, Mr. Bell, I don't even understand it. Where's the x? Well, it's just a constant. It's 5. Let's think. True or false? Do you agree or disagree? I'm going to ask questions even though it's a video, right? Even though I know you can't respond. Is that the same thing? Is 5 the same thing as 5 times 1? Yes, right? It totally is. So then let's extend it. Is that the same thing then as 5x to the 0 power? is x to the 0 power 1. Yes, right? So transitive property of equality. 5, if you wanted to, you could rewrite it as 5x to the 0. That 0 multiplies to the front. 5 times 0 is 0. So there you go. There's your derivative. It's 0. Another, maybe slightly easier way to think about it is to graph it. 1, 2, 3, 4, 5. So you've got a horizontal line. It's 5 units tall. Let's think about it. If I wanted to find the slope at this point, well, that constant is a horizontal line, so the slope is 0. What about if I wanted to find the derivative over here? Well, that's a horizontal line, and the slope of a horizontal line is still 0. What about right here? Again, it's a horizontal line, the slope is 0. What if my function, Mr. Belt, what if my function is y equals -1? Well, okay, then your horizontal line would be down here, and the slope would always be 0. Anytime you have a constant, a number, the derivative is always going to be 0. That kind of fills in this rule down here. The derivative of a constant is 0. Here's a tricky one that I think you may get on the next one. I don't remember if it's on the next page. I want to do it anyways. If you had something like pi cubed, the derivative, here's what a lot of students are going to do. A lot of people are going to say 3 pi squared. They're going to use the power rule for something that's not a power term, right? Pi cubed is not a variable. Pi cubed is a number. It's some constant, right? So the derivative is not a 3 pi squared. The derivative is just 0. Be careful. Sometimes I may be mean and I may try to trick you. Be careful. Don't let me trick you. Another one, if we did something like e to the 5th power. E is a constant, just like pi is a constant, except e is about 2.7. So the derivative is not 5e to the 4th. You can't use the power rule for stuff that's not a power term, right? E to the 5th is a constant, so the derivative is 0. Be careful. The derivative of any constant is 0 because the slope of any horizontal line is 0. Right, next. Let's get into this one. Here you've got a coefficient. You got that 5. If you need to, you could factor out that 5, and then you could take the derivative of just the variable part. You're like, okay, that 5's out in the front. I know I can do the derivative of x cubed. It's 3x squared. We already did it. And then lo and behold, that 5's still there. So then you get your answer as 15x squared. No, you don't really need to do that much work. Just think about it like this. The 5, you already have a coefficient. That exponent, when it multiplies down, it just multiplies into the coefficient you already had. So 5 times the 3 gets you the 15, and don't forget to decrease it by 1. Right? So if you have some extra coefficient, that's okay. You can factor it out if you want, but you don't need to. You just multiply that exponent down into it, and then decrease it by 1, right? So whatever this number is, multiplies, and you have c times n, and then don't forget to decrease the exponent by 1. Kind of went outside the box, sorry. All right, so we kind of got some 2 extra rules, kind of just as we go through it, and then we'll get the addition and subtraction one for the bottom. Here we go, one more. I've got the cube root of x on the bottom. The cube root of x would be a 1/3 power, and since that's on the bottom, here this original function, I'll just call it f, that original function would be x to the negative 1/3 power, right? That's some scary algebra skills. Hopefully you followed. The cube root is a 1/3 power. Since it's a cube root on the bottom, it's a negative 1/3 power. Right? If you had a square root on the bottom, it would be a negative 1/2. If you had a 5th root on the top, it would be a positive 1/5. Whenever you have a root, an nth root, it would just be the 1/nth power. And then if you have that term in the denominator, of course, the negative takes care of that. Now let's take the derivative. The negative 1/3 multiplies to the front, and be careful when you subtract 1. Be careful when you subtract 1 from the small fractions that become negative. Be careful when you subtract 1 from the negative numbers, and be doubly careful when you subtract from the negative fractions, right? Subtracting 1 isn't supposed to be hard, but you will make mistakes. Negative 1/3 minus 1 would be negative 4/3. So you could leave the answer like this, or if you wanted to, you could put it back into a similar form as to what the question started as, and you could put it as negative 1/3x to the 4/3. I really wouldn't put it back to a cube root. You could have an x to the 4th inside of the cube root. I just hate radicals. I would much rather you leave it with the 4/3 exponent than to bring back that cube root symbol. Ugh, it's just nasty. Okay, moving on. What happens, Mr. Bell, when we have addition or subtraction between pieces? Well, to answer your question, nothing happens. What you can do is you can just apply the derivative to each piece, and then you can just add or subtract the pieces together. Right here, it's really pretty simple. If you're taking the derivative of some function plus some other function, you can just take the derivative of the first piece and then add the derivative of the second piece. By the way, if you don't like this d dx notation, that's okay. You could write f prime plus g prime. Here it's just a command. It's telling you take the derivative with respect to x. That's telling you take the derivative of all this stuff. So you could write it as f prime plus g prime, or you could say, hey, it's the derivative of f plus the derivative of g. That is the same thing as f prime. This is the same thing as g prime. Either way is fine. And the same thing would be true for your subtraction. You could just take the derivative of the first piece, take the derivative of the second piece, and then just subtract them. Okay, let's do some examples. The derivative of this first part, 3 times 4, so it looks like 12x. Don't forget to decrease the power by 1. So there you go, 12x squared. That's the derivative of the first piece. Next one, I have a negative 5x squared. So that 2 is going to multiply to the front. Negative 10x. And then if that's quadratic, yep, 1 degree less is linear. There you go. And then the derivative of 7x. Ooh, let's do another example really quick. How about we do something, let's do something like 3x. And we can even do something like 3x plus 4, right? Think about it. 1, 2, 3, 4. Then it's got a slope of 3. For a linear function, the slope never changes. So I could ask you, hey, what's the derivative at 0? Oh, the slope at that point's 3. Or I could ask you, oh, over here when x is 2, what's the slope of this point? 3. What about over here? What's the slope of that point? 3, right? The slope at any, assuming your line is straight, the slope on any point of a line is always going to be the same thing because the slope of a line doesn't change. And that slope is always basically given to you for free. It's just the coefficient of the x, right? So for linear functions, all you need to do is look at the coefficient of the x. If you wanted to do the power rule, you could rewrite that as 3x to the first plus 4. So then if you wanted to take the derivative, that 1 multiplies to the front, and then 1 minus 1, come on pencil, stop it. 1 minus 1 is 0. The derivative of the 4 is 0, right? So that goes away. And then x to the 0 power is 1. So then you would end up getting, hey, the derivative, if this is your original function, the derivative is just 3, right? The slope of that line is always 3 no matter what part of the line you're looking at. So the derivative of linear terms is really easy. It's just the coefficient of the x. So now going back to this example, the derivative of plus 7x. If you think about that as being a linear function, you can even throw in the 3 if you want, but the slope of that line is just always going to be plus 7, and the 3 goes away. All right, the next one, you have to do some algebra first. And this is kind of what makes calculus a little bit notorious. A lot of the times the questions themselves aren't super difficult in terms of the calculus you need to do, but you may have to jump through some algebra hoops before you can do the calculus. Like here, you can't use your derivative rules because there's nothing that's a power term, right? All this stuff is divided by x. So what you're going to need to do is some math magic. You're just going to have to reduce this, simplify it, and then after you reduce it, then you can take the derivative. So let's see. You've got this fraction. The denominator is one piece, so I'm going to split it up. 5x to the 5th divided by x. That would be 5x to the 4th. Okay, the next term, I would have a negative 3x to the 4th over x. So that's going to reduce. You have negative 3x cubed. And then the last one, you have 4 over x. There's no x's that cancel, so you could leave that as 4 over x, or you could write it as plus 4x to the negative 1, right? You need to actually reduce it and make the whole thing look just like a sum and a difference of power terms before you can use the power rule. Okay, but now we're ready. Take the derivative, 4 times 5. Don't forget to subtract 1. This times negative 3. Don't forget to subtract 1. Negative 1 times 4. Don't forget to subtract 1. So you'd have a negative 2 as that exponent on the last term. And if you wanted to rewrite it, this last term, you could write as minus 4 over x squared. That would be fine. You could leave it with the negative exponents. I think a lot of the times on the homework you're going to see instructions that say don't leave rational exponents or don't leave negative exponents. Yeah, I don't really care, right? You can leave the negative exponents. Unless it says, like on the AP exam, don't leave negative exponents. Then yes, then you would need to rewrite it. But really, I don't care. All right, next page. Use the graph to estimate the slope of the line tangent to y equals x to the 2/3 power at the point 1, 1. Then verify my answer analytically. Okay, here we go. This is the point 1, 1. So what it's asking us to do first is to try to count the rise and the run, right? We have that tangent line. It's really kind of hard to see, but if you were to extend it, if you were to extend this grid, which I mean every year to just fix and to make a little bit nicer, but if you were to extend that graph, then the tangent line would actually go through that point, right? So it doesn't quite go through any of the nice quadrantal points. It goes through this one for sure, 1, 1. The next other really nice point is that one. So it wants you to estimate the slope of the line. So just count the rise and the run. So let's go for it. Slope. I see it goes up 2 over 3. So I'm thinking the slope of that line is 2/3. So that's the slope of the tangent line. That's the instantaneous rate of change. That's the derivative. Let's check it. Here, if I took the derivative, your 2/3 would multiply it to the front. 2/3 minus 1 would be negative 1/3. And then you could rewrite that as 2 over 3 x to the 1/3. And then what I would need to do, since this has x's, you need to plug in the x value for it. So y prime specifically, though, when x is 1, you'd have 2 over 3, 1 to the 1/3 power. What's the cube root of 1? Well, 1. 2 times, you just have 3 times 1, so 3 on the bottom. So look, it's going to end up confirming that we did end up getting 2/3. So if the value for the derivative tells you 2/3, that should mesh and verify what we could geometrically count with the rise and the run from the graph. Okay, find the derivative of 3x squared plus 5x minus 1, and then write the equation for the tangent line. Ooh, that's a very big topic, writing the equation of a tangent line. I think we did do some on the previous notes packet. But remember, we're always just going to want point-slope form. You don't have to get it into slope-intercept. Point-slope form is perfectly okay. And here you have the whole point, right? So there's the x1 coordinate. Here's the y coordinate. So that would get plugged in for the y1. So really, I kind of know a lot already. Y minus 7 equals, I don't know the m yet. That's going to come from the derivative. But I did have the x coordinate and I had the y coordinate for free. So you can plug them in. And then the last thing I need is the slope of that tangent line. So I have to take the derivative, and then I'm going to plug in 1 into the derivative. And then that numerical result that is going to tell me what the slope of the graph is, aka the slope of the tangent line, aka the derivative. All right, so let's go for it. The derivative here, 2 times 3 would be 6. The derivative of 5x would be 5. The derivative of the constant is 0. So there is your derivative function, right? There's your derivative. And then it says, and write this equation for the tangent line. We're almost there. We just need to figure out what number it plugs in. So evaluate it. We have an x value. Plug in 1 for it. Here, I guess you should put y prime of 1. 6 times 1 plus 5. Looks like 11. So then, since the slope at that point is 11, you can go ahead and plug it in. Getting it into slope-intercept form would only be 2 extra steps. You could distribute the 11, and then you could add the 7 over. But unless the question specifically tells you that your answer needs to get to slope-intercept form, point slope is okay, right? Always just leave the answer, right? The question even tells you, leave the answer in point slope form. Is it hard to do the remaining algebra steps? Look, You have 11x minus 11, add the 7. Oh, I forgot the x. That was bad. Then you could add the 7 over, so you'd have 11x minus 4. Is it hard to do the remaining 2 steps of algebra? No. Are you going to get it right probably 99% of the time? Yes. But we know sometimes when we're rushing, especially on quizzes and tests and at the end of the year, the AP exam, sometimes when we're rushing, that's when we make silly mistakes. And you don't want to risk making a silly mistake in these last 2 steps. It's completely unnecessary. The point slope version is a perfectly acceptable answer. There is no need to go farther unless it specifically asks you to, right? Just stop when it's safe. Going farther is just risk. There's really no benefit, so stop at point slope, right? So equations of a tangent line. If this question, right, let's pretend it had only said at the point where x equals 1. So if it only gave me the x value, how would I have found the y value? That's easy. If you have the function and you have the x value, you would just plug in the x value into the original function. So you have 3, 1 squared plus 5 times 1 minus 7. So you have 3 plus 5 minus 1. Ooh, that's where they got the 7. So if they only give you the x, then you can find that y value by just plugging into the original, and you have to find the m value, the slope, by plugging in to the derivative. Sometimes it's nice, and sometimes they give you both. That's great. One less thing for you to do. But if they only give you the x, that's okay. It's not the end of the world. Plug into the original. That's how you can get the y coordinate. Okay, let's shift gears now, and then let's start doing some trig stuff. Right? Let's do probably these 2 examples, then I'm probably going to have to pause because I've got another class coming up here in like 20 minutes. So let's do these 2 examples, and then I'll pick up with the next video. Here we go. You can look up proofs for sine, and you can look up proofs for cosine on YouTube on your own. It's not important that you know why the derivatives are the way they are. It's just important that you know what they are. So here we go. It's a little bit tricky. The derivative of sine is cosine. Right? That's not too bad. The derivative of sine is cosine. And I know what you're thinking now. You're like, Mr. Bell, please, 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 can the derivative of cosine be sine? Right? Can they just switch back and forth? Almost. It's not quite that easy. I wish it was. It would make my life a whole lot easier. The derivative of sine is cosine. That's nice. But the derivative of cosine is negative sine. Okay, so just be careful. Those are 2 facts that you need to know. The derivative of sine is cosine, then the derivative of cosine is negative sine. Let's think about the cyclical nature of this, though. If I had a sine, the derivative would be cosine. The derivative of cosine is negative sine. The derivative of negative sine, just think about having that extra -1 coefficient. The derivative of a negative cosine, well, the derivative of sine is cosine, so you'd have the negative cosine. Negative cosine. And let's think, what's the derivative of negative cosine? Well, the derivative of the cosine would be negative sine, and then negative sine is going to spit you right back to sine, right? So there's this cyclical nature to it. I wish it would just go this to this and then back. That would be nice. But unfortunately, all of your co-functions, all of the trig functions that start with a c are going to end up having a negative when you take the derivative, right? So the derivative of sine is cosine. The derivative of cosine is negative sine. However it is that you memorize stuff, those 2 facts must be memorized. They got to be in your brain. We're going to get the other 4 trig functions at a later date, but for now, sine and cosine, not terrible, but a little bit annoying. Could be worse, though. Here we go. 2 examples, then I'm going to stop. The derivative of this first term is going to be 12x. How lovely. And then we have a plus 5 cosine. I know the derivative, like here, I'm just, look, copy the 5, that's fine. And the derivative of a positive cosine is a negative sine. So there you go. 12x minus 5 sine of x. All right, and then this last one, you've got this extra negative. You should distribute it first. So this original function, here, rewrite it. This original function is negative cosine of x minus sine of x. Just take this and distribute it. Now let's go through and do these derivatives. The derivative of negative cosine is a positive sign. The two negatives will cancel. And then the derivative of a negative sign is your negative cosine. So there's your two answers for those two. I'll pick up with the next example in the next video.